So this is my student's PhD student Ishraq's work, and he couldn't be here due to some visa issues. So I'm presenting his work. So this work is done in collaboration with the National Research Council of Canada. And this is basically very preliminary work for one project that we just started a year ago. So as you can see, the work is about biodegradable substrate-based microwave resonators. It's for liquid sensing. So first, I'm going to talk a little bit about the motivation for the work. And so microwave resonators, maybe some of you are very familiar with. They're very simple structures, and they're based on basically microwave transmission line based. These are microwave transmission line based sensors. So the benefit of using this type of sensor, as you can see from the the sensor design, they are very simple designs, so they're very easy to fabricate. They provide non-invasive real-time sensing, and also they're compatible with CMOS processes, so that helps to actually make make it integrated with other circuitry. So microwave resonator-based sensors are nothing new, so they've been used quite a lot in many applications like communication and medical applications, environmental sensing. So usually when microwave resonator-based sensors are made, they're made on conventional substrate that has very low losses, something like Rogers board, which is a very popular type of board because they have low losses. Usually these microwave substrates are rigid, so they're not very compatible for flexible application. But these days there are also many works where they use flexible substrate like polyimide, PET. However, these substrate, although they're flexible, they're not biodegradable, and basically they're polymer based, but they're also very difficult to recycle. And the recycle process is pretty expensive. So since we are using a lot of sensors these days, so there is a great demand for using biodegradable substrates or materials for sensors. So one of the area where actually Canadian Research Council is looking at is using biodegradable substrate for many sensor application. In fact, the research center that we are working on, they are also making all those RFID chip for our Canadian passport, and they're making those also on biodegradable substrate. So, so in this project, we were actually looking into using biodegradable substrate for microwave resonator-based sensor. So there are a lot of biodegradable substrates. Cellulose is a very popular one. Now, the main challenge, you can see the sensor structure is simple. However, the main problem to use, biodegradable substrate is these substrates are pretty lossy. So the response you get out of them, this resonance response, they have very low quality factor. So it's difficult to achieve high sensitivity in those sensing application. But otherwise, in terms of fabrication, there is not much difficulty in them. One area we are also looking into is when we're making these resonator-based sensors is also if we can make the process of making resonator more sustainable. So usually these microwave resonators are made with conventional microfabrication process. So you have these metal layers all over your substrate, and then you use conventional lithography to make them, which actually is not very environment friendly. So if we can use printed electronics technology to make this conductive pattern on the substrate, we don't have to use any lithography process. It's a low temperature process. So all of it makes the process of making the resonator pretty sustainable. So basically, the whole purpose is to make this the device and the fabrication process all pretty sustainable. So if you go into literature, you're going to find also a lot of microwave resonator-based sensors for liquid sensing. So these are some applications, and most of them you will see that they're made on Rogers board, and they have different configuration. So the first one is actually it's an active sensor, so they actually use an active filter to increase the sensitivity, but that also makes them, they require basically external power source. The next example where is actually a passive one, but you actually put some holder where you put the liquid, and that holder basically is difficult to clean. So when you put different liquid in them, you have cross-contamination. Also, they use a quality factor as a sensing parameter, which is also not a very good parameter of choice to measure. So, they all have some pros and cons, but all I wanted to show is, you can see most of them are made on, Rogers board. The last example where they actually make it on a cellulose film. However, only the resonator part is made on the cellulose film, but the transmission line that is coupled to the resonator is still made on a Rogers board, and only the cellulose which contains the resonator is placed on that Rogers board. So this is again not biodegradable substrate. And there is also another problem in this one where they printed the resonator. This also sort of shrink the cellulose film. So as I mentioned, our objective was to print the microwave resonator on a biodegradable substrate. And the first application or the preliminary thing we were looking at is actually sensing different liquid and different concentration of a liquid, which is isopropanol solution. So what we did, we basically designed some very simple split ring resonator. So it's basically the simplest structure you can think of. And then we simulated that in HFSS, did a lot of parametric simulation to come up with a size and different coupling gaps and all of those things. Then we basically printed that resonator on a cellulose film. As a ground plane for now, we were using copper tape, but that's also not the best solution. We could actually apply some silver as a ground plane with doctor blading or some other methods. And then once the resonator is built, we actually use some small tube in a microfluidic channel over the resonator to pass different fluid. And then basically we monitor the resonant frequency and the amplitude of the response. So just to give you a little bit brief overview about ring resonators. So split ring resonators, as I mentioned, they're very simple structure. These are, you can see they can be circular or they can be rectangular, and they are actually coupled to full or half wavelength transmission line. Usually the standing waves are created in these ring resonators, and you only get the resonance when total length of this loop is somewhere an integer multiple of the wavelength. So usually to make it sensitive to something, you create a slit in your loop or in your ring resonator, and that's really the most sensitive area of for sensing. So whenever if you're trying to sense some material, you usually try to place it on the slit. So how the coupling, so there is a coupling gap between your transmission line and the resonator, and the distance or the coupling gap really makes a big difference. So usually when you design them, you do a parametric analysis to figure out what is the best coupling gap. You can also have, other than a single loop, you can have double loop resonator. So you can have a lot of variation in the design, but overall, these are very simple structures, and there is nothing really complicated about them. So for our work, we choose a rectangular ring resonator. These are just some equation that we use to, come up with the dimension for, we actually designed it for the prime or first mode frequency, 1.2 gigahertz. So, we use these equations to figure out the dimensions for our design. And for the coupling gap, we really did a parametric analysis in HFSS to come up with the best coupling gap. Also, we found that if the transmission, so you can actually place the transmission line, in the same line with the slit or, in different other places. But we found that for this structure, basically, this is the best configuration to get good sensitivity. So this basically shows all the, different size and parameters for our design. And on the right-hand side, that literally shows one of the resonators that is built and connected to a VNA. So you can see basically the cellulose is transparent. So the color you are seeing is literally from the copper tape that we use for this as a ground plane. So these are some of the results. So first, we try to see how much, how well our fabrication went. So we compare and in this case, we are actually measuring in the second mode. So around 2.4 gigahertz. So in the simulation, we first compare the simulation with the measurement. Just is the bare resonator. There is nothing placed on them. And you can see the measurement is quite a bit different than the simulation. And part of the reason is because when we connect those connectors for measurement with our VNA, so we need to apply the silver epoxy, and all those things really makes a big difference in terms of this deviation. And then we measure the resonant frequency after we place the tube on the slit area. And you can see also placing the tube lowers the quality factor. You can see that from lowering the amplitude. It also affects the resonant frequency too. And I mean, even simulation shows that that is supposed to happen. So first test we do is just to see whether we can differentiate between different liquid materials. So we pass different liquid material like isopropanol, vinegar, ethanol, water through the tube, and we see that the resonant frequency changes. The quality factor changes not that much, but resonant frequency does shift. And the other experiment we did is we pass different IPA solution through the tube and see how much the resonant frequency shifts as well. And we also see with concentration of that IPA or isopropanol solution how much the frequency changes. So you can see it's not if you look at the sensitivity yet, it's not like very great because it's really from the result, you can see that we only have around 13 megahertz variation for 100% change of the isopropanol concentration. So this is not very good enough because the type of limit of detection we also got from this around 25% IPA. But this is very preliminary work, and as I mentioned, the first sensor structure we used, and this is only to see whether the cellulose type of substrate can be used. This is very simple structure we used. So currently we are actually going for some more complicated structure and more differential type of measurement to get a better sensitivity in this design. So I guess that's pretty much it, what I wanted to show from this preliminary work. So as I mentioned, one of the big challenge also about using this biodegradable substrate is figuring out their dielectric laws and basically the dielectric properties, because these are not conventionally used dielectric substrate. So there is, if you look in the literature, there are different values for them, but those are mostly characterized at low frequency. And when we also measured them at high frequency with our dielectric probe, our values are not also very stable. There are a lot of challenges to measure the dielectric properties at gigahertz range. So this is one of the problems we face, because whenever we are also doing the simulation, we needed to know all these dielectric properties of the substrate. And whenever we were measuring them with dielectric probe, sometimes we get different values on different days, and it's just because when we use dielectric probe, you need a very thick, layer of material to measure something more than 1 centimeter to measure the dielectric properties properly. But whenever we are purchasing this substrate, most of them are, the commercial ones, the most, thickness we get are around 0.5 millimeter. So, with that thin substrate, I'm not even sure the dielectric properties we're measuring is really the, true dielectric properties. So one thing we are also now doing, instead of using the cellulose acetate that we buy commercially, we are trying to just make our own substrate, like cellulose acetate, so we can actually make thicker substrate and have good idea about the dielectric properties, because that really is very much important when you are and also doing your simulation and stuff. So yeah, so that's the last remark I wanted to make. But there is a lot of, I guess, potential for these type of devices. If we can make a low loss substrate. So I'm really happy to take any questions you have.